Log on, tune in, find out. Another good idea from Cambridge.
Who will talk on moduli spaces of Gorenstein Quasi-Homogenous surface singularities.
So I would like to thank the organizers of the whole program for inviting me and also for the opportunity to give this talk. It in some sense fits with what the program is about, and in some sense it doesn't. We'll see. So the title is about Gorenstein Quasi-Homogenous surface singularities, but I'll start from the other end and then sorry about that. I'll start from the other end and then we'll get to the singularities later on. Now, start with spin bundles on Riemann surfaces. Riemann surface then. Spin bundle is a complex line bundle on the surface such that the tensor product of the bundle L with itself is the canonical bundle or the holomorphic cotangent bundle of the surface. Right. And okay, the definition in this form appeared somewhat later, but the earliest appearance of spin bundles is as theta functions very early on in the 19th century, I suppose. And I want to quote a result which in that form appeared in the 70s on the moduli space of spin bundles on all possible surfaces of the Riemann surface structure. And in the modern kind of form, it was formulated in papers of Attier and Mumford, and different papers at the same year in the same journal, or the different approaches to the same problem. And one of the statements is that this space has two connected components. So if we think of two spin bundles as equivalent, if one is a pullback of the other under a homeomorphism of the surface, then we can ask ourselves how many equivalence classes are there, or how many connected components, and the answer is there are two different connected components, so two kinds of spin bundles, which can't be obtained one from the other by homomorphism of the surface. More precisely, what it says is, so if we have our Riemann surface as a quotient by function group of the hyperbolic plane of the unit disk, then every spin bundle corresponds to a lift of the function group gamma, which is in PSL to R, into the twofold cover SL to R. Where the lift is just a subgroup in SL to R, such that the projection restricted to this subgroup gives us an isomorphism. So gamma star is just a subgroup in SL to R, which is exactly isomorphic to the Fuchsian group underneath. Topologically, PSL to R is just the open solid torus. And the cover by SL to R is just the way a circle covers a circle. And we can define a map. So for every element in the Fuchsian group gamma, we can look where the pre-image of this element is in SL to R, and depending on which half of SL to R it is in, we can assign a 0 or 1 to this element. Right? So for every element in gamma, we can read off from the lift a 0 or 1, which tells us in which position it is. So we could, for example, say the matrices with positive trace is 1/2, and the matrices with a negative trace is the other half. So what we get a map on the fundamental group of our surface, and this map can be pushed down to the homology, the first homology of the surface, and we get a map on the first homology, which turns out to be a quadratic form. And And the two components of the moduli space of spin bundles are distinguished by the quadratic forms are distinguished by their arc invariant, and it turns out that the components of the moduli space of the spin bundles are distinguished by the arc invariant of this quadratic form that we obtain from the spin bundle. And the arc, should I say anything about the arc invariant, or is it familiar? Yes? Yeah.
Well, once upon a time, I forgot.
Right, I mean, there are two equivalence classes of quadratic forms over Z, over 2Z, and the alpha invariant is basically the value which appears most often among the values of the quadratic form. Right? If it's 0, it's a 1 class, and if it's 1, it's the other class.
When they're talking about theta characteristics, which I think is one of the things that Thea and Mumford talked about, does it correspond to them being even and odd?
I'm not sure.
I think there's something about the number of even theta characteristics is something, and the number of odd ones is something else. I think that's a formula of either a T or a Mumford or both.
Right. Okay. So, how can these be generalized? Or different ways thinking of similar problems. One, I didn't say this at the beginning, but the result of it here in Mumford is for compact Riemann surfaces. So we can think about what happens on non-compact Riemann surfaces if we have punctures or holes, or the situation where our function group has elliptic elements so that we get an orbifold, and maybe holes and punctures and all sorts of things, so it's kind of most general kind of surface we can think of. And another direction is to think about higher spin bundles. So we have in the definition that the second tensor power of our spin bundle is a canonic bundle. What about the higher powers? For some m. Or we can think about all these generalizations together. Higher spin bundles on orbifolds or non-compact Riemann surfaces. And it's not just generalization for the sake of generalization. These objects do appear in different contexts in mathematics. If we look at the higher spin structures or spin bundles on Riemann surfaces and we allow punctures, this moduli space appears in physical applications in models of two-dimensional gravitation, and keywords are like Witten hypothesis, and there was a lot of studying these moduli spaces around this kind of problem. And for example, in the work of Jarvis, Moore and Weinhold around 2000. Later, after that, on the other hand, if we look at orbifolds, Riemann orbifolds, so where we have the quotient which is compact but which has, where the function group has elliptic elements. This leads us back to the title, to the Gorenstein Quasi-Homogenous surface singularities. So these kind of bundles appear in the construction of these singularities. Okay. how do these bundles come into the construction? So we start off with a simply connected Riemannian surface, hyperbolic plane, CQ1 of C, and we have a group of orthomorphisms of the Riemann surface, and we have a complex line bundle on this surface, and the group is discrete and co-compact. And we have an action of the group gamma on the surface and on the bundle in a impossible way. If this set of data satisfies the following conditions, the action of gamma is free on the bundle without the zero section. And if we take a normal subgroup of finite index, which gets rid of the torsion, which acts freely on our Riemann surface U, and we divide by the action of this group, so we get a bundle on the Riemann surface U by gamma prime, then this line bundle we want it to be negative.
Is that quotient assumed to be compact, U mod gamma prime?
Yeah, gamma was co-compact, so we take finite index subgroup. Yeah. Can everybody see this board? Yeah. Then we construct a zero section of this bundle so that we get an isolated singularity at where the zero section was. And then take the quotient by the action of the what remains of gamma, the quotient gamma by gamma prime. And then we get some complex surface depending on U, gamma, and L. With an isolated singularity. And there were many people studying this type of singularities in the 70s and early 80s, so there are probably more people that should be written there. And the result is that then the resulting surface isolated singularity is quasi-homogeneous surface singularity, and all such singularities are obtained in this way from some choice of the simply connected Riemann surface subgroup of automorphisms and the bundle. Or more precisely, the action of the group gamma on the bundle. The bundle itself without the action is just a trivial bundle, but it's the action that we are interested in. So these are the quasi-homogeneous surface singularities. Which ones of them are Gorenstein? So the singularity that we get is Gorenstein if and only if there is such M, such that the M tensor power of the bundle is the tangent bundle of our Riemannian surface, and the equivalence is with respect to the gamma action. So we can also say that the corresponding bundle on the compact Riemann surface, M tensor power, is equivalent to the tangent bundle. Now, whether we look at the, so this one we call M co-spin bundle, because we have the tangent bundle, not the cotangent bundle, but pretty much the same from the classification point of view, whether we classify the co-spin bundles or the spin bundles. Right. And this is the result of Dolgotchev and Neumann, and it's also a result of Watanabe, which includes higher dimensions as well. So the higher spin bundles or co-spin bundles come in here into the construction of the singularities. And we can ask the same question, what is the moduli space of such bundles, and then translate it into kind of moduli space of those singularities. So if we have a bundle, then in the same way as the spin bundles, two spin bundles correspond to lifts into the two-fold cover, M spin bundles correspond to lifts into M-fold cover. Okay, where the lift has the same meaning, group upstairs, which is isomorphic to the group downstairs under the projection. And if you have such a lift, then again we can subdivide the m-fold cover into m regions and assign to every element element of a number between 0 and n minus 1, saying in which region it is. And so we get a function on the fundamental group of our surface, which is isomorphic to gamma, and we'll call this function R function because R invariants were somewhere there, and instead of the R invariant we have the whole function now, which we'll use to classify the bundles.
It doesn't descend to the abelianization of the fundamental group now?
Not without problems. And it certainly doesn't give you a quadratic form, which one could then classify, so one has to kind of work more at this level. So it's not as complex a description as in the classical case. So in the classical case, we said it's a quadratic form, and then we can classify the quadratic form by its R invariant. But let's see how more kind of hands-on approach to that, how it comes about. Have a lift of a surface group, in the case of compact Riemann surfaces, into SL2R. We have a set of generators of the group gamma, or the fundamental group. Then the quadratic form that we have described gives us gives us 2G numbers 0, 1, which describe the bundle in terms of this set of generators. Now, if we want to go from one set of generators to another, we do it by means of den twists. So, the group of autohomomorphs of P is generated by den twists. What kind of dentist do we have at hand to jump from one set of generators to another? We can twist in one of the curves that correspond to A1, B1, then we get a twist of this kind. We can twist in a curve which connects to pairs of handles, and we get a twist of this form, where this is some conjugate of A1 and some conjugate of this element, and so on. You don't really want to know what exactly is there, but it is something of this form. So what do these dentists do with the values of our R function, the function on the homology? One can work that out. One can translate properties of the m-fold cover of PSL to R into properties of this R function on the homology or later on the fundamental group, and one can work out what happens to the values of the R function under then twists. Now, if we look at the first kind of then twist, what we see, we can use it to play kind of Euclidean algorithm on these two values. So play them against each other so that we can get every pair to the form where one is in the pair is 0 and another is the greatest common divisor of the values we started with. All right. Now, if one plays with them a little bit more, then one can see that we can use the second type of then twist to play one pair against another. So to decrease values in one pair using values in the other one, and then playing these pairs against each other, we can jump from one set of generators to another to get to a standard set of values for any form, for any R function. So we can reduce it to the form 0 and all ones, or 0, 0 and all ones, depending on which one we started with. So even though we started here with numbers from between 0 and m, we're able to reduce them again to zeros and ones. Oh no, here we are in the Z2. No, here we are in the classical situation, so here we started with zeros and ones. Okay. Right. And so these two standard forms are the two different components. So if we arrive at one standard form, we are in one component. We started in one component. If we arrive at the other, we are in the other component. And we can show that these two standard forms are not equivalent to each other. For example, we know that that should be the case because the alpha invariant is different, so they shouldn't be. But we can also show that the alpha invariant remains invariant under the dentist, so we can't use dentist to get from one form to another. Right, so that shows us that we have these two components of the moduli space in the classic case of two spin bundles on compact Riemann surfaces. Now, what happens in the case of a Riemannian orbifold and a higher spin bundle, M spin bundle on it? First of all, as a remark, we don't always have such M spin bundles on a given Riemannian orbifold. It depends on the things like signature of the orbifold and so on. So, if orbifold is of genus G and P1 to PR are orders of classes of elliptic elements that we have in the group, then for M spin bundles to exist on such an orbifold, certain divisibility conditions have to be satisfied, which are that the orders of the elliptic elements are prime with the M, which is the level of the spin bundle, and also that this number has to be 0 modulo M, which is kind of Euler class condition. And in the classical case where we have no elliptic elements and we have two spin bundle, this reduces to the condition that 2g minus 2 has to be 0 modulo 2, which is of course always satisfied, so that's why this condition doesn't appear in the classical case.
So Pi are the orders of the stabilizer groups of points of the orbital.
Yes. So now we have a set of generators of gamma, or set of generators of the orbifold fundamental group of P. So these are the ones corresponding to the handles, and these are the ones corresponding to the elliptic elements, or to the orbifold points. And from the lift of gamma into the m-fold cover, we get this R function on the fundamental group, or orbifold fundamental group. So if we write down the values on a particular set of generators, and we work from one set of generators to the other, again using the band twists. So we have the same two types of band twists on the handles and between two handles, and then we have an additional twist where we kind of twist a handle around an orbifold point. So that so what does it do to these values? So what we see here is that the value on the orbifold point can affect the values on the handles. Right? So we can use these to modify the others. So there's this additional type of transformation that we have. And it turns out that if G is larger than 1, we can use these 3 types of den twists again to reduce it to this form. So even though we started with the ones between 0 and n minus 1, we still end up with entries between 0 and 1. Okay. I make a condition here that G is larger than 1 because the second kind of den twist that we had was between 2 handles. So if G is 1, then we don't have this den twist to help us. So we can't reduce it to this simple form. And we end up with more connected components in this case. Obviously, in the classical case, G equal 1 is not a hyperbolic, doesn't give us a hyperbolic surface, so that case doesn't appear. But here, if we have enough elliptic points, then it could still be a hyperbolic orbifold. So the case not really more complicated, more involved. Just have more things to consider and write down. Okay. So we don't have a quadratic form and we don't have the half invariant of the quadratic form, but we can still do all the things that we could do in the classical case. And if we have such a function on the fundamental group, which comes from a m-spin bundle on our orbifold, we'll define an invariant which will classify such R functions. Concentrate on the case of genus at least 2. So we say that the half invariant is 0 if m is even and for some set of generators we get that this is 0 modulo 2. So in every pair at least one of them is 1. Then this invariant determines the connected component of the moduli space, which component we are in. So if we prescribe the signature of the orbifold, the genus and the orders of the orbifold points, and the level of the spin bundle, the high spin bundle, and we assume that they satisfy those divisibility conditions, so the m spin bundles do exist on such an orbifold. In the case of genus at least 2, then the space of all m spin bundles on orbifolds of this given signature has two connected components if m is even. And one connected component if m is odd. And each connected component is homeomorphic to a quotient of a ball of dimension 6g minus 6 plus 2r by a discrete group action, where this of course comes somehow from the Teichner space, and this is some subgroup of the group mod acting on the Teichner space of finite index. And what I have forgotten to say at the beginning is that it's all joint work with Sergei Nathanson from Moscow, including this theorem here. This is the case G at least 2, and in the case G equal 1, one can also work out how many components there are, and then the number of components is high, it's equal to the number of divisors of common divisors of G and numbers P1 minus 1 and PR minus 1 and M. So more components and more complicated number theoretical kind of discussion, but essentially it's the same kind of method for that. One can do similar things for the situation when one has punctures and holes in addition to the orbifold points. That would just complicate the notation and complicate the statement of results, but essentially it's again the same technique. Yeah, thank you for your attention.
Any questions?
I have a few questions. So the first is that the title was about these quasi-homogeneous Gorenstein surface singularities.
Right.
So there's a map from the moduli space of these m-spin things, which you talked about it in the board on the left there.
Yeah.
So there's a map from the moduli space you're studying to the moduli space of these Gorenstein surface singularities.
Mm-hmm.
And I guess that map is surjective.
It's 1-to-1.
Oh, it's 1-to-1.
Yes, yeah.
Oh, okay.
The singularities correspond 1-to-1 to lifts of function groups.
Oh, okay.
Compact function groups.
Oh, I I didn't realize that. So you said, yeah, on the left there, you just said that the map is surjective.
This doesn't talk about Gorenstein ones, it talks about all of them,
okay.
yeah.
Sorry.
For the
I
Gorenstein ones,
misunderstood.
yeah, it is one-to-one, yes.
Oh, okay. Is it one-to-one only for the Gorenstein ones?
No, it is one-to-one here as well, up to an appropriate isomorphism.
So then the theorem you stated here, so you have a subgroup of the modular group, right? So that subgroup is what we should call, in this case, I guess for this signature, it's the M spin mapping class group.
Yeah.
Except there's a distinction between two different notions of, I guess in the classical case I'm familiar with, the spin mapping class group as a subgroup of index 2, and the spin mapping class group is actually a Z mod 2 extension of the mapping class group. And in terms of the fundamental group of the moduli stack for spin Riemann surfaces, the fundamental group of the moduli stack is actually the Z mod 2 extension. So is something similar going on here? There's really a moduli stack of these M spin bundles on orbifolds, and this somehow the fundamental group of the M spin stack should be an extension of the modular group.
And the group I'm talking about here is just a subgroup of the mod group.
Yeah, what is the index of the subgroup?
It's finite index. It's a subgroup which basically preserves the invariant, the alpha invariant. I'm not sure whether we worked out the index. And I mean, I'm not algebraic geometry person, so if you can tell me anything about the M spin stock and the group, then I would be very happy. But I don't know the answer to that question.
I'll have to think and maybe ask you some more questions later.
Okay.
More questions now? Okay, so can we thank Anna again?